Dariusz Strugarek is talking about modeling of systematic effects in SLR observations to swarm satellites for determination of global geodetic parameters.
Okay, so in the beginning, I would like to acknowledge the co-authors of my presentation and the members of the IOB, Dr. Daniel Arnold and Professor Ajahn Yagi, who contributed for our tests. Since recent decade, we can observe a rapid emergence of the active low Earth orbit satellites. I mean here Swarm constellation, Sentinel constellation, Grace constellation, and those type of satellites. Many of them, fortunately, are equipped with the satellite laser ranging retroflectors, which the examples are shown on the right side, and also with the GNSS receivers, Dariusz receiver, which are used for precise orbit determination. What is interesting, I looked in the ILRS quarterly report cards, and the normal points to those types of satellites orbiting at the low Earth orbit constitute about 76% of all observations provided by ILRS. The remaining ones are spherical geodetic like Radio's or high orbit satellites. And those types of observations, observations to LEOs, are nominally or commonly used for the orbit validation only. Also, from the perspective of LEO precise orbit determination products, we can observe a rapid emergence and development for the LEO POD. I mean here by considering multi-technique combinations, for example, GNSS with DORIS, improvements within particular techniques, including also SLR, as well as developments of the LEO POD strategies and procedures. These improvements lets us to a very great consistency between POD products from, for example, GNSS with the SLR observations, which reach the level of 1 centimeter or even better. Nevertheless, when we analyze SLR residuals, so the difference between computed and observed ranges between stations and satellites, when we do not model systematic effects, we may see some offsets of residuals or the elevation angle dependency, which was also shown in the previous presentation. That's why we try to use those types of observations, so SLR measurements to LEOs, to improve the consistency between LEO products and SLR measurements. And also we test to determine station coordinates and other global geodetic parameters by using SLR to LEOs, including swarm satellites, by investigating different approaches for modeling of systematic effects. I mean here range biases and tropospheric delay corrections. And in our test, we used over 1 year of data for SLR measurements to swarm satellites with the a priori products provided by different product sources. And here in the figure you can see the SLR stations which contribute the observations to our test. There were 32 of them. And we prepare 3 scenarios. The first one, the rest solution, in which we do not model any systematic effect. Then a range bias solution, RB here, in which we calculate the range biases, and TRP solution with the consideration of tropospheric delay modeling. And within 2 different approaches, 1-day parameters, which we analyze as validation of the LEO satellites, and 7-day solutions for the determination of parameters, and also to compare our parameters with the Ledgers-based estimates. Here in the left-hand side, you can see the example of the parameters that we calculated based solely from SLR to swarm satellites, median values of range biases within a left-hand side of the figure. For the example, stations and swarm A, B, and C satellites. And the right side here, we can see the tropospheric bias corrections. Those types of parameters are, of course, station specific. However, within the swarm constellation, the values are quite close with each other when we consider range biases or tropospheric biases. Also, on the right side, we can see the comparison of estimated solutions, so the range biases, tropospheric biases from swarms, and compared to the same estimates from LEGIOS to solution in this right side. So the range biases, when we compare them to the tropospheric biases, are more scattered, within the range of plus minus 15 millimeters, or for some stations, the values are even lower. The tropospheric biases are analogical, but less scattered. Here we have the range of about plus minus 8 millimeter, and the tropospheric corrections are consistent within the LEGIOS-based estimates, which can be seen on the right-hand side plots. Next, I've compared different modeling of systematic effects, so those range biases and TRP solutions, and look for the residuals. Top row shows the case when we have no modeling of systematic effects, middle row when we estimate only range biases daily solution, and we can see that the offset of residual is reduced successfully. However, still we have the elevation angle dependency, whereas in the case of the tropospheric biases, both cases, so offset and dependencies of to the elevation angles, are successfully removed. Also, we try to verify it or avoid in our solution that the parameters shouldn't absorb the orbital effects in our parameters. That's why we verify our solution by comparing different orbit products, and figures show the histogram of residuals for the orbits provided by IOP with the kinematic solution, ESA reduced dynamic solution, and IOP reduced dynamic solution. And what we can see when we use the troposphere modeling, the SLR observations are more consistent within different orbit solutions. We have more residuals within the range of plus minus 10 millimeters. And introducing tropospheric biases allows us for the comparison of orbit quality between different orbital products. Next topic, so we try to estimate other parameters, station coordinates based solely on SLR measurements to swarm satellites, and figure shows the estimates of the northeast and up component for the two group of stations, 32 stations on the core sites. For the solution, when we include range biases, tropospheric bias, and without modeling of any effects, compared to the solution based on the LEGIOS 1 and 2 data with tropospheric estimates. What we can see that the reparability of SLR station coordinates of swarm-only solution is at the very similar level to the LEGIOS one, at the level of 13 and 7 millimeters for the up and horizontal components. So yeah, we have really nice consistency at the level of 1 to 3 millimeter with the LEGIOS-based estimates. Here, slide presents the time series for the selected two stations, northeast and up component for our test. We can also see here the nice consistency, the millimeter level consistency between particular solutions. However, the range biases or without modeling of any systematic effects are less consistent than the solutions when we introduce the tropospheric biases. I also would like to mention our other test, other solution in which we try to use SLR measurements for multi-satellite combination. In this case, we use SLR measurements to different types of satellites, 9 LEOs, including swarm satellites, 3 spherical geodetic like GEOS 1, 2, and LARES, and Galileo constellations for calculation of global geodetic parameters in station coordinates. And we analyze the one-year period with considering range biases and weighting of observations, normal equation systems. Figure shows the estimates of the station coordinates for the three tested solution based only on the LEGIOS 1-2 satellites, on 9 LEO satellites, and a weighted multi-satellite combination. And what we can see that the positioning of all stations from the combination of LEO only and weighted multi-satellite combinations we have the accuracy at the level of less than 18 and 10 millimeters for the up and horizontal components respectively, and we can observe the improvement of the formal errors from the multi-satellite solution even reaches the level even 50%. Here we can see the geocenter motion X, Y, and Z components from the three tested solutions, and we can see consistency between our LEO-only and combined solution with the estimates based on LAGEOS 1 and 2 data. And pole coordinates and a LEO-D parameter from tested three solutions. Also, we have the very nice consistency with LAGEOS-based estimates based on multi-satellite combinations, whereas in the case of LOD parameter, there's 3 times improvement of the multi-satellite combinations compared to the LAGEOS-based ones. To sum up, modeling of systematic effects in SLR observations to swarms, such as station satellite range biases, reduced only the offset of residuals, whereas the tropospheric biases comprises not only the deficiencies in the tropospheric modeling, but also the offset of residuals and other elevation-dependent effects. And this approach even further reduces the LEO residuals and allows for the comparison of the LEO POD products. Also, we can calculate SLR station coordinates with the reparability at the level of 10 to 13 millimeters and 7 millimeters, depending on the solution, and enables us to calculate other parameters, geocenter motion, pole coordinates, and length of day, which estimates show high consistency with the LAGEOS only estimates. And thank you for your attention.
Thank you, Darek. Very interesting and important presentation. Do you have any questions to Darek or comments, even online? You showed the EOP, yes. The improvement of EOP dramatically.
Yes.
I'm wondering why only LOD improvement of LOD is so significant.
The improvement it's related with the geometry observations because the LAGEOS 1 and 2 solution is based only on 2 satellites. Mm-hmm. For example, there are so many observations on low variation angles or zenith angles. However, when we add other types of satellites, I mean here LEOs and GNSS LEO, so the observation geometry gets improved, and that's what I think is the reason that we have the improvement of the LEOD parameter.
Okay, thank you. No more questions. Okay, thank you, Darek.
Thanks.